All right, so hopefully you found our discussion on the different bolt limit states very interesting. Let's see how we're going to apply these equations into solving a problem in which we look at the design strength of a tension member, but subjected to all the tension limit states, yielding, fracture, and block shear, as well as all our bolt limit states and constructability concerns. Woohoo, an example problem. We love to do some calculations, and hopefully it's no different when we look at it for bolt limit states. So go ahead and familiarize yourself with the connection. We have two plate members that are being pulled apart, and then we have a double lap splice crossing the two plate members as shown. So we have the PL 1/2 by 8" member. I just want to point out that there's a gap in there, and so that's what the black shaded portion is. And then we have two PL 1/4 by 8 members crossing that gap and connecting the two 1/2" members together. A36 is being used for all the plate members. We have 7/8" diameter bolts. They're going to be ASTM A325 bolts, so that means they're group A. We'll use standard size holes, and we have class A surfaces. We are asked to compute the design strength of the members and connections shown if the connection is to be designed as a bearing type connection. The first thing I want to do is I want to find all the possible limit states, and this is quite a list. So we have yielding of the gross section, we have fracture of the net section, block shear, so these are all our member limit states. Then we have the bearing failure at the bolt holes and tear out failure at the bolt holes. We have bolt shear, minimum edge and spacing requirements, as well as maximum edge and spacing requirements. Alright, so we'll dive right into the calculations. We have the yielding, the fracture, and the block shear calculations. So go ahead, and if you want to review them, you can. Hopefully everything is making sense here, and it should be kind of just a recap of some of those previous limit states. I'm going to go ahead and fast forward through them, but if you need to, take it slow and check them out and refresh your memory. So now we're on to our bolt related limit states. So first we want to talk about the bearing failure at the bolt holes. So we said bearing failure was going to be phi(Rn) equals phi times 2.4 times the diameter of the bolt times the thickness times F sub u. Phi is going to be 0.75 for bearing failure. The diameter of the bolt was given to us as 7/8 inch from the problem statement. Now we have to make a decision on what the thickness will be in F sub u. F sub u will be 58 KSI because we had A36 steel. T is the thickness of the plate, and we have the 1/2 inch by 8 inch member, and then we have the 2/4 inch by 8 inch splice plates. So we can consider both of them. We have to consider both of them in the design of the connection. So we have the thickness is either going to be a 1/2 inch or 2 times the 1/4 inch, which is also a 1/2 inch. So we'll find that the bearing failure, the bearing strength of both the splice plate and the regular 1/2 by 8 inch plate will be the same value. Doing the calculations, we get that phi(Rn) is 45.7 kips. This is per bolt hole or per bolt. So just keep that in mind. We're coming up with sort of nominal resistance for little portions of the connection for each bolt hole. Next, I want to look at tear out failure of the holes. Now, like we did with bearing, we have to consider both the 1/4 inch splice plate and the 1/2 inch plate members. So recalling our formula, phi(Rn) is going to be phi times 1.2 times L sub c times T times F sub u, where phi is going to be 0.75. Again, for a rupture limit state, F sub u will be 58 KSI because we have A36 steel. For the 1/2 inch plate, my thickness is going to be T, and now I have to calculate my clear distance L sub c for the 1/2 inch plate. Now, if you've noticed, I've numbered my bolt holes. So I have bolts number 1, 2, 3, and 4 in the figure above. So I need to look at the failure for each bolt hole in terms of its clear length. So I'll start with bolt holes 1 and 2. For the 1/2 inch member, as I pull on the 1/2 inch member, I'm worried that bolts 1 and 2 as you know, as I pull on the 1/2 inch member, bolts 1 and 2 are going to bear on it, and we have the danger of ripping bolts 1 and 2 into bolt holes 3 and 4. So my clear length L sub C is what I've shown there in green. For bolts 1 and 2, L sub C is going to be the spacing, or the stagger, or 3 inches, minus 1 hole diameter, so a 1/2 a hole on either side. So we can get this hole diameter by taking 7/8 inch plus a 1/16 of an inch, since we're less than a 1 inch diameter bolt, and that'll give us 2.0625 inches. We can also get the hole diameter directly from table J 3.3. We have to do the same for bolts 3 and 4, and so bolts 3 and 4, we're worried that 3 and 4 are going to rip out the back edge of the 1/2 inch by 8 inch plate member. So for bolts 3 and 4, I calculate L sub C as that edge distance, 1.125 inches, minus 1/2 a hole diameter. Again, 1/2 of the hole will be 15/16 of an inch. And again, I got this from table J 3.3. And that'll calculate to be 0.656 inches. Now I need to plug in my values of L sub C for both bolts 1 and 2 and 3 and 4 into the equation above for phi Rn. So plugging in phi as 0.75, 1.2 times L sub C of 2.0625 inches times the thickness, which is a 1/2 inch, times 58 ksi. I get that for bolts 1 and 2, phi Rn calculates to be 53.8 kips per bolt. I'll do the same for bolts 3 and 4, and I see that my calculations for bolts 3 and 4 gives me phi Rn equals 17.1 kips per bolt hole. Now I can't just stop there. I also have to consider my double splice plates. Okay, and so because the edge distances and the spacings might differ for each of the members, we need to check both members in this connection. So for the 1/4 inch splice plates, my thickness is going to be a 1/4 inch, but I have 2 splice plates, so 1/4 inch times 2, so that'll give me a total of 1/2 inch for the double splice plates. Now when I look at bolts 1 and 2, now I'm worried for the splice plates that bolts 1 and 2 are going to rip out the right edge of the splice plates. So I've shaded that there in red above in the figure. So I see for bolts 1 and 2, my L sub C is going to be that distance, the clear distance from the edge of bolts 1 and 2 to the edge of the splice plate. So that's going to be 2 inches minus 1/2 of the hole diameter, 15/16 inch, which gives me 1.531 inches. Again, plugging that into phi Rn gives me 40.0 kips per bolt hole. I have to repeat this for bolts 3 and 4, but for bolts 3 and 4 for the splice plates, I see that bolts 3 and 4 would rip into bolts 1 and 2. So bolts 3 and 4 will rip along that green path that we already calculated. So L sub C will be once again 2.0625 inches for that green path, leading to phi Rn of 53.8 kips per bolt hole. So hopefully you followed where we got all the numbers for these calculations. So this gives our calculations for the tear-out strength. So we got the bearing strength, we got the tear-out strength. Now we want to look at bolt shear. So I said table 7-1 was useful for bolt shear. So I need to go back to the information given to me in the problem statement. Since no information was given on whether or not the threads were included or excluded from the shear plane, I have to assume that the threads are included in the shear plane. So I'll assume that we have a type N connection. It was given to me that we were using A325 bolts, which is a group A type bolt. And then I have to analyze my connection for the shear condition. So I see that I have a double splice plate on the left-hand side, and then I have a regular 1/2 inch by 8 inch plate on the right-hand side. And I'm going to just sketch that out. You can go back and look at the connection again. But I see that my splice plates are pulling to the left, and then my other plate member would be pulling to the right. And so it looks to me in this case that we have two shear planes. So we have a shear plane. The total shear in the bolt would be half of the total amount of load. So I see that I'm in double shear, so this is going to be D. So moving through the table, I see I'm in group A. I'm in a thread condition N. I'm in double shear D for a 7/8 inch diameter bolt. My capacity is 48.7 kips per bolt hole. And so now I have the total shear capacity of my bolt. If you don't want to just take the table's word for it, you can go through and calculate this yourself. So if we were to look at table J3.2, we would see that for an A325, a group A bolt with an N style connection with the threads in the plane of shear, my nominal shear stress would be 54 KSI. I multiply that times my phi of 0.75 times pi over 4 times the diameter squared of the bolt, so that's my area of my bolt, times 2 because I have double shear. So this would also give me phi Rn equals 48.7 kips per bolt. So now we can use this table 7-1 with a little bit more confidence that we know where the number comes from. Finally, let's take a look at our minimum edge and spacing requirements, and then we'll look at our maximum spacing requirements. For our minimum edge and spacing requirements, we said that the minimum spacing has to be at least 2 2/3 times the diameter of the bolt. So I would say that S has to be greater than 2 2/3 times the diameter of the bolt. So this means that the spacing in my connection needs to be greater than 2 2/3 times 7/8 inch, which means that the spacing has to be larger than 2.33 inches. If I return to the connection drawing, I see that in the longitudinal direction, my longitudinal spacing is 3 inches. So I have an S of 3 inches, and my gauge spacing across the width of the connection is 4 inches. So both 3 inches and 4 inches is greater than 2.33 inches, so I'm okay from my minimum spacing standpoint. Next, I have to look at the minimum edge distance requirement. So I go to table J3.4 for a 7/8 inch diameter bolt. I can read the value right from the table that the minimum edge distance needs to be 1 1/8 inch. So I'll go ahead and highlight those values in the table. My minimum edge distance has to be greater than or equal to 1 1/8 inch. My calculations for shear tearout, I calculated those edge distances, and my lowest edge distance was for the PL 1/2 by 8 inch member, which had an edge distance of 1.125 inches. This is in fact equal to 1 1/8 inch, so my connection would pass. For my 1/4 inch splice plates, the edge distance was 2 inches, and so that was also greater than 1.125 inches, and so it is also okay. Or I can just say, well, I had longer edge distance, so I know that it'll be okay. We'll now do our maximum spacing requirements, which are stipulated by AISC J3.5. So the first requirement is that the edge distance has to be less than or equal to 12 times the thickness of the thinner plate, and this edge distance had to be less than or equal to 6 inches. So we see that our edge distances were 2 inches and 1 1/8 inch. If I do 12 times the 1/4 inch splice plate, I get 3 inches. I also have 6 inches. Both my PL 1/2 by 8 member and my PL 1/4 by 8 inch splice plates will meet my requirements. So I see for the 1/2 by 8 inch member, I had an edge distance of 1.125 inches. For the 1/4 by 8 inch splice plates, I had an edge distance of 2 inches. And so both of those do not exceed the maximum value. I have the ore in there. We also have to look at the edge distance from the top and bottom of the plates. So from the top and bottom, that edge distance was 2 inches for both plate types. So I also meet the requirements in the transverse direction or the gauge direction of our connection spacing. Finally, we have to look at the spacing limits between bolts. You have to just make an assumption here. We weren't given anything in the problem statement, so I'll just assume that we're using painted steel. So this says that the spacing has to be less than 24 times the thickness and that it has to be less than or equal to 12 inches. For the 1/2 inch by 8 inch plate member, our spacing was 3 inches. For the 1/4 inch by 8 inch member, our spacing was also 3 inches. And so we meet the requirements for that. And now we're ready to come up with the capacity of our connection. Now, it's important that we remember that the total connection strength, VPN, is the sum of the individual resistance strengths for each bolt or bolt hole in the connection. So I've created this sort of little table to highlight the 4 different bolts I had. Remember, I numbered the bolts 1, 2, 3, and 4. So I've gone ahead and I've summarized the information in this for the 1/2 inch plate member for bearing and tear out, for the 1/4 inch plate member for bearing and tear out, for bolt shear, which is just one value for all the bolts, and I need to determine the minimum resistance from each of them. So moving across my rows, for bolt 1, I see my lowest resistance is the 1/4 inch plate for tear out. So I use a value of 40.0 kips. For bolts 3 and 4, I see that my limiting strength is the tear out of the 1/2 inch plate. So that was 17.1 kips. And so now I've taken those values and I've added them together. So for bolts 1 and 2, I use 40 kips. For bolts 3 and 4, I use 17.1 kips. And I get a total of 114.2 kips for my entire connection from my bolt limit states. Lastly, I compare this strength to all my limit states. So for yielding, I had 130 kips. For fracture, 131. Block shear gave me 131.3 kips. Bolt limit states gave me 114.2. So I see that for all my limit states, my bolt limit state controlled my design. And so VPN for the entire connection would be 114.2 kips. I also see that I met all my minimum edge and spacing requirements as well as my maximum spacing requirements. Alright, so I hope you enjoyed applying the equations for bearing strength, tear out strength, and for bolt shear, and to calculate the total amount of strength for from our bolt limit states. I know sometimes these connections can be tedious, but it's important that we get them correct because we always know that the devil's in the details and connections are definitely the details of a structure and we need to make sure they're correct. Talk to many an engineer, they'll always tell you connections are one of the hardest things to do because there's so many different things you have to consider as you're designing. So good luck. We'll do another example in the next class. See you soon.